So now we're going to talk about loop invariants. And so the idea here is that we're going to use these loop invariants to prove correctness of a loop with respect to our pre and post conditions. So we're going to look at a while loop, and entry into this while loop is restricted by a condition G, which is called the guard. So this while loop looks something like kind of this setup right here, where we have our precondition, we have while, our guard, and then some kind of statements within here. So statements in the body of the loop. None of these are going to lead outside of the loop, and then we end the while. So this is our structure. So now let's talk about what it means to be correct for this a loop. We're going to say a loop is defined as correct with respect to pre and post conditions if and only if, whenever the algorithm variables satisfy the precondition for the loop, and the loop terminates after a finite number of steps. The algorithm variables satisfy the post condition. Right, so whenever your algorithm variables satisfy the precondition and the loop has to terminate after a finite number of steps, you want to make sure that the algorithm variables satisfy the post condition. So now let's look at loop invariant. It's kind of what we've been building up to. So I'm going to define loop invariant. A loop invariant is a predicate with domain a set of integers. So remember, predicates have variables in them, they're not statements, which satisfies the following condition. So for each iteration of the loop if the predicate is true before the iteration, then it is true after the iteration. So again, this idea kind of connects to induction. It connects to induction because you're saying if it's true for one value, then it's true for the next value. So in this case, we're talking about iterations instead of values, but if it's true for this one, then it's true for the next one. All right, so next time we'll go into more detail about these loop invariants.